Howdy folks, Mr. Reed here, and welcome to one more question. So, I'm going to be taking a look at this concept of the unit circle today. So, if you've wondered what the unit circle is, or maybe where it comes from, and what its use is for trig, then you're in the right place. Let's get to it. Okay, so this one's a little bit funny, because you could just print off a unit circle and use it, and I guess if somebody tells you what things represent anyway, that's probably good enough. But I have a problem with doing that a lot of the times with the people that I try to teach. So what I like to do is try to come up with how you would get the unit circle. And then from there, you can kind of maybe get why you don't have to memorize the whole thing, even if you wanted to know it. So what is the unit circle? Well, first of all, the unit circle is kind of what it sounds like if you know what a single unit would be. So the unit circle is the circle of radius 1 centered at the origin. So if this went out to positive 1 in that location, then this would be called the unit circle. Now, the unit circle is especially helpful to trig because of a relationship that we can build when we throw a triangle in there whose I guess you could say outer vertex, or one of the vertices of a right angled triangle is on the origin, but one of the other ones is on the outer edge of this unit circle. So one of the things that you kind of need to know to get started here is the equation of a circle. And if it's not something that you've bumped into before, it will seem a little bit weird. So what I'm going to do instead is, if we were to blow that circle up the way that it is drawn right now, if I had the origin right about there, then what I could do is at any particular location around the outside of the circle, whether it be here or whether it be here or wherever, I could draw a line that connects my origin to that outer point. Could do one there too, so I'll just kind of show you with that. And once I've done that, since I have a couple axes here, I have my x-axis and I have my y-axis, when it drops down to the axis, I could make it drop down and hit at a 90-degree angle. So I could, I guess, drop in altitude or something like that. And the idea is that if I call this point x comma y on the outside of the circle, then it would be true that the length of this bottom part here would be x, and the length of this part here would be y. So, what you probably do know, even if you don't know the equation of a circle, is Pythagorean theorem. So for a right angle triangle, we can say that the square of both of those legs added together would be equal to the square of the hypotenuse. But we've defined this as being the unit circle. So it has a radius of 1 unit, or 1. So it would be 1 squared. So we get an equation here of x squared plus y squared is equal to 1. Now, that's true for this point x comma y that I've drawn in, but that point could have been this one. This could have been our x comma y. And then we could draw things, and you might get into an argument where it's negative x if you did, but it actually is x. But if you were thinking, oh, but it's actually a negative value, since it becomes squared when finding the length of the hypotenuse, it doesn't actually matter. So x squared plus y squared is equal to 1 is the equation of our circle, and for us it's a unit circle centered at the origin. All right, so we can go a little bit further. If inside of that unit circle, that angle that we have made right here inside of the triangle that's in our unit circle, if I called that thing theta, then it would be true that the cosine of theta would be equal to adjacent over hypotenuse. So most people, before they've gotten to the point where they discover some things about the unit circle, have probably done your 3 primary trig ratios inside of a right angle triangle. Some of you might have even memorized this as SOHCAHTOA. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and TOA is tan is equal to opposite over adjacent. So in this particular case, we would have adjacent over hypotenuse. But since dividing by 1 doesn't really do anything in particular, we would get that that is equal to just x. Likewise, sine theta is going to be equal to just y. So, oddly enough, the coordinates x comma y, x, y, are also cosine theta comma sine theta, which means that the answers or the values of our trig ratios for cosine and sine are actually listed on the outside of this particular circle. Actually, the coordinates at every single point along this circle are going to be the cosine and the sine of the angle in standard position that has a terminal arm that cuts through the circle at that particular value. Now, even if you had an angle where it was going through some outside point, like way up here, and so we connect this line here, there is an equivalent point here where it actually is going to intersect with the unit circle, and so the unit circle will give us all of the trig ratios that we need, even if it's some larger hypotenuse triangle that we're currently discussing. That doesn't really matter. So that's why people use the unit circle, is because it can give us all of these trig ratios, or at least it's going to help us with ones that we consider special angles, and they'll show up quite a bit. All right, so here, that's basically the idea of the unit circle. So now what we need to do is actually get some labeling around the unit circle. So I'm not going to steal someone else's image. There are plenty of really nice images on the internet, and you should go find one right now if you're watching my video. So look up, Google unit circle. People have really nice layouts for those. And so what I'm going to do is tell you how you would come up with the labels around the outside of those. So first things first, the easy ones. Here, whoopee, here, 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 here. How would you come up with those values? It's 1 unit away from the origin along the positive x-axis, 1, 0, because you want 1 in the positive x direction and none in the y direction. The coordinate axes are actually really easy, because this one just goes 1 in the y, this one goes 1 backwards along the x, and this one goes 1 down along the y. So we can label those ones really, really easily. That means that the cosine of 0 is 1, because this would be our 0-degree angle if we drew it in standard position. Its cosine is 1, its sine is 0. If we have the 90-degree angle in standard position, which would be this one right here, then its cosine is 0, its sine is 1. And that's why it's nice to kind of have this information organized this way, because we can get the sine and the cosine values related to something geometrically that allows us to recall them a lot easier than if we were just to memorize the list of values. So that's good. What I'm going to now introduce are 2 special triangles, is what I'm going to call them. So the first one's going to be an equilateral triangle. So my equilateral triangle is going to have a 60-degree angle in all 3 of its corners, all 3 of the vertex locations, 60-degree angles everywhere. So now I'm going to take a bisecting line, and I'm going to drop it right down. What that's going to do is it's going to bisect the angle, but it's also going to bisect the side that's down at the bottom. I also am going to pick a side length for my equilateral triangle. Now, I usually pick a side length of 1, just because I envision that this is actually an arm that's inside of my unit circle. So that is kind of my equivalent there, is that this is going into this position. So that's what I'll do here. I'm going to call it 1. It actually works out nicer if you say that it has a length of 2. The values in the mid steps look a little tidier, but I'm just going to say 1, which means that down here I actually have a length of 1/2. What we're going to do from there is actually use a little bit of Pythagorean theorem again, because this would be a right angle, to say that the 1/2 squared plus, and I'm going to call it, I don't know, let's call it C just for the time being. No, probably not C. Let's call it D. D squared. So, oops, sorry, that would just be a D. Should have erased it instead of scribbling, but my apologies. So 1/2 squared plus D squared is going to be equal to 1 squared. So that means that 1/4 plus D squared is equal to 1, or D squared is equal to 3/4, which if I take my square root top and bottom means I'll get technically plus or minus, but if I'm thinking of it as just a length, instead of a y coordinate, I guess you could say, or so it could have been up, could have been down. If I just do my 60-degree angle first in this standard position, then really I only want to describe the positive root there. So it's going to be root 3 over 2. So what that means is the length of d is root 3 over 2. So I have this little triangle that has 1 as a side length, 1/2 as a side length, and root 3 over 2 as a side length. So if I wanted to describe for this angle, the 60 degrees in the corner, the cosine would be adjacent over hypotenuse. So what I can say then is that the cosine of 60 degrees is equal to 1/2 divided by 1, which is just 1/2. If I wanted to describe to somebody the sine of 60 degrees, then that's equal to opposite, which is the d value, which we said was root 3 over 2, divided by 1. So it would be root 3 over 2 for the sine of 60. Now, we can also get the cosine and the sine of 30 from this same triangle because it actually is just the other angle that's up in this corner. So that's going to be a 30-degree angle because we bisected a 60-degree angle. So when we bisect that 60-degree angle to make it 30, it's the same triangle, just the opposite side is now the 1/2, and the adjacent side is the root 3 over 2. So we would have cosine of 30 is equal to root 3 over 2, and the sine of 30 is equal to 1/2. So we have a set of nice trig ratios for two, I guess, important special angles. So the only other angle that I'm going to cover is the 45-degree angle, which we're going to make an isosceles triangle of 45, 45, 90 for that one. I'll do that in just a second. But first I'm going to talk a little bit about some symmetry. Because the 60-degree angle here is symmetrical with an angle of 120 here, and the 30-degree angle is symmetrical with a one of 150 over here. And then, if I go and do symmetry across the x-axis, the 150-degree angle is symmetrical with the, it has a mirror, I guess, across the x-axis, if you don't know what I mean by symmetrical, with the 210-degree angle, and the 120-degree angle is symmetrical with the 240-degree angle here. And then I could use either the stuff in quadrant number 3 or quadrant number 1 to determine symmetry for this next one. But I have the one here, which is at 300, and the one here, which is going to be at 330. So basically, even though I only figured out 4 trig ratios for 2 different angles, what I've really done is figured out these 2 trig ratios for all 8 of these locations. So if I wanted to know what is the x and the y value at this position, well, the x value is going to be the same but the opposite sign as to the x value it's symmetrical with on the other side there. So I would be able to say that, oh, this point, because it's the 60-degree angle, is coordinates 1/2 comma root 3 over 2. So that means that this point over here is coordinates of, oh, that's silly, coordinates of negative 1/2 and root 3 over 2. So what that ends up meaning, which is pretty cool, is that we can just plop the positives and negatives according to where they are in Cartesian space. So you are probably very aware of the fact that stuff up here in this quadrant is positive x, positive y, negative x, positive y, negative x, negative y, and positive x, negative y. If that's true, then you just use these same symmetrical coordinates, but you put the right sign with it to be in the right quadrant. And that's all you really have to do. So I usually tell people that I teach that you are only really memorizing what's going on in quadrant 1, and then you're going to use symmetry to understand what's going on in the other quadrants. If you don't have to memorize this stuff at all, that's great, but it's still a good idea, I think, to know why or how you could come up with this stuff. And being able to recall it quickly while working on a problem isn't ever going to make things harder. It can only make things a little bit easier. All right, so as I said, I'm going to talk about that other triangle, which would be 45, Oh, why did I draw it like this? That's a bad triangle. Sorry about that, folks. So let's go like this. 45, 45, 90. All right, so this one I'm going to say has a length of 1 here and 1. I'm going to say has a length of 1 here. And then because this and this have the same side length, I'll just call them A for the time being. That would mean that a squared plus a squared is equal to 1 squared. 2a squareds then is equal to 1, or a squared is just equal to 1/2. If I take the square root of that, that's going to give me 1 over root 2, and depending on who you talk to, this is an unsimplified form of something that has a radical in it. We need to rationalize the denominator. So if we do that, we would get multiplied by root 2 down bottom and up top, because we don't want to change the value. So we're really just multiplying by 1. So you get root 2 over 2. I didn't pull the negative into it this time because, like last time, I'm discussing that this is the 45-degree angle specifically built inside of my unit circle. So now that we know that, this one is root 2 over 2, and this one is also root 2 over 2 because they're the same in that 45-degree angle. This is an isosceles triangle. So that means that the cosine of 45 is equal to, and then it's going to be adjacent over the hypotenuse, which is just going to give me root 2 over 2. And the sine of 45 degrees is going to give me the same thing because the opposite side is the same length, also over the hypotenuse of 1. So we would get our coordinates at the 45-degree angle, which in turn, because of symmetry, gives us the coordinates at the 135-degree angle, which in turn gives us at the 225 as well as the 315. So we would have all those coordinates of all the coordinate axes and the special angles that are just reflections of 30, 45, and 60. That's basically the entire unit circle. You can do a little bit more with it. For instance, if you want to know tan, in our original triangle that we were looking at the beginning, we said that cosine was x and sine was y because we said it was x over 1. Well, in this case, it's actually tan is y over x. So since y is sine and x is cosine, we can actually define tan as being sine over cosine. And so we can take the two coordinates that we've already memorized, divide them to give you what's going on for tan. So I think I'm going to leave it at that. That's kind of how you would put together a unit circle on your own. If all you're doing is using one, then I guess that gives you a little bit of background of where this thing came from. If you're memorizing it, though, this is really helpful because it will allow you to kind of see why these patterns are there and be able to use the patterns in symmetry to memorize a lot less than you could if you just went all the way around. One of the trickier things will be doing this all in radians instead, especially if you're not comfortable with it, but that's just going to take some time in memorization. So hopefully you found that one helpful. If you did, like, subscribe, and as always, take care, folks.